Hi everybody, this is Evergreen Hacker. We are at leetcode.com and this will be the video about the last exercise from weekly contest number 4, and the task is called Evaluate Division. So let's go there and I'll give you a few seconds to read through the description and examples. Okay, so it seems to be super easy now. We have to just give the answers for what's already given to us. Oh no, it's not that easy. We are given A over B and B over C, but sometimes we may be asked about A over C. So we have to reason somehow that if we have B here and B here, then those two equations can be combined in order to get A over C, so that let's say B will be represented as 3.0 multiplied by C, and then we substitute this B with 3C basically, and then we would have A over C equals 6, kind of. Yeah, because 3 will go from here to 2, and we will have 2 multiplied by 3, which is 6. Yeah, and then what else do we have? We have A over A. So those guys are not here anywhere, but they are obvious because that will be 1 for all cases. And then X over X is unknown, yeah, because we don't have X mentioned anywhere. So those guys are just corner cases. We can deal with them quite easily without doing any extra math. We just check if we know those literals like A or X, and if we know them, then just return 1. If we don't, return -1. So what else do we have here? A over E. We know A, but we don't know E anywhere. So we just return -1 for that. And then what else? B over A. Oh, that's interesting. So we have A over B, but we don't have B over A. So we just have to invert this equation so that it becomes B over A and it becomes 1 over 2, which is 0.5. Okay. Input is always valid. You may assume that there's no division by 0. Okay. So that's good thing. It means that we can easily invert those guys. We will never have 0 here, basically, in the right side. So that we can invert all of those guys, and we can do that as the first step. Just invert all of them, or not invert. We can do even better. We can say that A equals to 2B, and then we can invert so that B over A equals 0.5, and we would say that B equals 0.5A. So we can represent all of the literals through other literals. Yeah, and for some of those guys we will have duplicates. Well, not exact duplicates, but duplicates on the left side. Like B can be 0.5A, and also B can be 3C. So when we move C here, it will be 3C. So that if we know that B is at the same time 0.5A and it's also 3C, then we can easily solve this. Okay, so what's the plan then? The first step we will do is do those equations. So let's just outline it here. Given that we have to calculate A, B, and C. Well, not exactly calculate, but it's represent A, B, and C. And in which ways? So we would okay, so then how do we store all that? We can have a hash map indexed by literals, and then we would have an array of those guys. Or yes, even better, we can have a hash map over hash maps, so that on the first level we would have A, and on the second level we would have B, and the result would be like 2. And then for A, we would have 1. Anything else? So let's just put minuses here. Or not minuses, but like stars. That we covered them. Then for B, we would have this, and this. So let's, okay, and then C. So we would have this hash of hashes, and we would be able to quickly check if we have a path from A to B, let's say. Yeah, actually, this looks a lot like a graph problem. We are searching for a path, not necessarily the shortest path, just any path would work. Let's say the first one. And so we are searching for a path from an A to a C if we need to find A over C. So first, we go to A over B, and then we go to B over C. Yeah, and kind of we immediately get that. We get A over C. Yeah, this was easy because A and B and B and C are on the first locations here, like first entries in the sub-hash maps. We can move them a little bit, like as if we are sorting by indices. And we can try it again. So we would have A over A. It brings us nowhere. And then we would try again. So we are kind of starting with A, trying A first, doesn't work. Then we go to B. Then now we are trying with A again. Here we can have like a set of scene literals so that we don't go to A at all, because we've already seen A here, so we don't need to make loops. So then B, we also have B in the scene. Actually, same thing as here. We don't even go to AA because we already have A. Let's say scene is A in this case. And then here we add B to scene. Okay. Then we don't go to A, we don't go to B, and then we go to C, and that's what we need. Oh, yeah, by the way, we can just use this great Yeah, we can use this great feature of hash maps that we can index sub hash maps by C directly. So we can just check if A has C here on the second level of hash maps. If not, then we're going over all of the values, like we go over A, then over B. But then for B, we can directly get the C because we have C there in the second level. So we don't even need to go through A and B at all. Yeah, we go straight there. So we kind of already are getting closer to algorithm. So let's say A, how we call that? C is not in hash. So then go through all keys of hash A, right? And yeah, but here, oops, C is in hash B, so we just go straight to hash AC. Yeah, not A, it's B this time. Okay, so let's try something harder. Let's try B over A, because we don't have B over A in the exact form here. Will it work? Let's see. B, so scene is B. Then we go to BA, so we know that it's here, so we can directly go there. Yeah, 2.5. Okay, where is it? Yeah, 2.5. Okay, then A over E. Let's check. A, so scene is A. Then we are going through A and B. Yeah, actually we would have to explore almost the full tree here, or at least all the leaves which are accessible from A. Yeah, in this case it's not tree, it's a graph, but still. So we go to B because we don't need to go to A. And then from B we go to where? To A again? No. To B? No. To C. Then from C nowhere. We don't have because we don't go to B and we don't go to C. They are all in scene, so we just stay there. Then where else can B go? B goes also to A and B. We are not checking them. Okay, that's it. So then A also goes to A itself. That's it. So we are just checking this path then. So we ended up not finding E anywhere, and we just return -1 for this case. Okay, and for X, let's try for X. X is not in hash at all, so we return -1 immediately. Okay, so seems that we know what we are doing here. Let's try to go that. So let me just code that stuff here. So not code, just okay. So 2 element arrays. equations, two element trace, then values, and this array, it's not array, it has the same size as this guy. So it's the first element, that's the second element, and also it's the first, I'm sorry, the first and the second. Then queries here. Okay, so now we would have to go through all of the queries basically. For query in queries, and what it asks us to find A over C. So self find path A C basically, but in this case it would be query 0, query 1. Path. If path is none, then not return. We would have to put it in an array. Actually, let's return, yeah, self find path x0, x1 for x in queries. That would be much easier to write the same stuff. And find path should be, yeah, we should rewrite that find path a bit differently. Yeah, so the find path should know that it should return -1. So that in this case it's not find path, it's solve. So yeah. Then before that we would have to prepare our super cool two-layered hash map. Let's do that. We are doing self prepare hash map, and we are passing equations there and values. Then that's pretty much it. So we've prepared that stuff. We've prepared that, and then the solve part will reason based on a hash map. So prep hash will store hash map somewhere in the depth of the object. Say self hash equals, yeah. Yeah, I don't think it has to do something else. So let's just implement the missing functions, methods, solve, it gets self, and then it gets, let's call them A and B, shall we? So that it calculates, solves A over B. I don't know. Yeah, I called it like that, but you can call them P1, P2. And then we have to do this scene thing. But what I'm thinking right now, if we use a scene and we try to solve A over A, we will not be able to, because scene already has A there, and we will just not go to this branch ever. So it's better to cover this case right here. If A equals to B, then we have to return either -1 or +1, depending on if A is present in hash. Return 1, or say 1.0, if A is present there. and else we return -1. So that's it. We covered those two cases. And since we have them already, we don't need to calculate those. So then we would have to implement this sing thing. So let's just say it's an empty set at the beginning, or it has an A. Yeah, let's say it has an A, because we've started with that always before. And while yeah, B is not in scene, yeah, if we haven't seen it yet, then what are we doing? We are trying two things. First is this case. If B is in self hash A, then just go directly there. Whoops. Then we say return. We have to know the result, right? So let's call it k, because it will be a coefficient like this guy. 2 is a k, 3 is a k, 0.5 is a k. So k is 1 at the beginning, and we just return k multiplied by this. So then it means that we don't even need this check here. Yeah. Okay. So then if we don't have B there, then we would have to go to all of the keys of hash A, like this thing. Else do something over all of the keys. Solve all of the keys for key in self hash of A. And then, yeah, probably we don't even need this while here. But I'm thinking maybe we don't need a recursion. Let's try doing the recursion now. And then we are still solving for B, but we change the first argument. So the first argument, instead of A, it will be a key inside a hash A. So it will be this guy, this guy, this guy, this guy. But now we have to use this scene somehow. And if key is not in scene, then do that. If result is -1, then no, we cannot really do that either, because we may have valid result -1, right? So it should return something like none to represent a fault. So let's return none. Then let's check if it's not none. If res is not none, then it means that we have a solution, and we just return k multiplied by res, because we already have k here, and then we solved for a subpath, so we just append a weight of this path, of this edge. We still haven't decided what we do with this scene guy, because we have to pass the scene to solve. What I'm thinking is that we can just pass extra argument, which will be this scene, and at the beginning it will be none, and then if it's none, then we will create that. Otherwise, we pass it. Yeah, it may work. Okay, let's do this. So we are passing scene. If scene is none, then we create that, and then here we pass scene. So here we solve for subpath, starting with some a prime, and then we check if we reached the end. Like if a prime is b, then we ended up at the node which we wanted to find. So we return 1. Otherwise, we are setting the k to 1 and trying to see if we have b straight in the nodes directly connected to us. If it is there, then we just return the edge weight multiplied by the yeah, but we already had this k equals to 1 here, so I'm not sure if we need it. Probably we don't. Yeah, we don't need k, so we just return this, which is the weight of the edge from a to b, and then here, if we don't have it in direct connections, then we just go over all of the connections and try to solve for a prime in this case. So it should work, but we are not doing anything with scene. So here we have to say that we visited this guy, scene of B, yeah, I'm sorry, and B. We add B there, but we no, not B, key. So key is somewhere in between. So let's just quickly write the summary here. If we have some path, or usually it's written like this, yeah. If it's directly connected, so there are multiple cases there. A is B, then A is directly connected with B, and then A is directly connected with some key, which is somehow connected with B. So for this case, it's just 1. For this case, it's the edge weight. And for this case, we just return res. Yeah, so this is the problem. We have to multiply it by the weight of A to key. Yeah. So we have to add this weight and then this weight. So this weight will be returned by solve, and this weight we know. So we have it here from A to key, because key, yeah, we go through all of the keys in A. Okay, so then let's just double check. We're solving for k and b, and we are passing scene and we are adding key there. And then if result is not none, then we are returning that stuff. But we also have to return none. When? Basically when we have nothing else to return. Return none. Yeah. Okay. Then now let's do this solve wrapper, which, yeah, it has almost the same set of arguments. We can remove this none from here. We can say that we call self solve a, b, and then none. Or even better, we can just do it here, set of a. Yeah, so just create it there. And then we have to analyze the result. If result is none, then return -1. And else just return result. That's it. So remove this stuff, replace solve with solve wrapper. Or yeah, let's keep it solve, but then this one will be a recursion. Okay, so now we have to implement this prep hash. Self, then equations and values. So let's start with empty hash, and then we are just going through all of the equations. For equations, it have to have an index because values and equations are of the same size and they share indices. For e in x range of len of values, because it's easier to write values, we are doing what? So equation is this guy and value is this guy. So we know that it will be a and b, and this will be 2. This and this. And what are we doing is that we say hash hash equation 0. Yeah, we would have to use default hash here. Default dict with lambda something. Let's fill it in a sec. With equation 1 equals val. And then this equals 1 over val. And just in case, let's do this to make them doubles. Okay, so with what we are having here, it's a lambda which should return a hash so that when we access things which are missing, it will return a hash to us, and then we will just add um, this guy there. Yeah. Let's import from collections, import default ticket. Okay. So let's go through a quick example. We can have that stuff, and we will ask for A over C. Yeah. Okay. A over C. Prep hash. So we go to hash. Oh no, we haven't returned anything. So let's return hash. Okay. Hash is a default ticket. Then for I in X range, so it will be in this case 0 and then 1, because we have only 2 elements in those arrays. And then this guy, it will be A and B and 2 at the beginning, so that's it. Then hash will be A, B, 2, and here it will be B, A, 0.5. And then for I equals 1, it will be different. It will be B and C. And here it will be 3. So B to C is 3, and C to B third. And then we return hash. We set self hash to this. So self hash would be this. So those are obviously strings. Yeah, but let's just put it this way. Now we are solving for those guys. So it will be A and C at the beginning, A and C, also strings, then B and A, and so on. So we are interested in A and C. So solve will be called with, oh, we still have C in here, we don't need to. So solve will be called with A and C. And we are calling the rec with A, B, which are A and C, and the set of A. And this is special case. Okay. So now let's debug it. We have A equals A, we have B equals C, we have C equals just A, nothing else. And then if A equals B, that's not the case. If B is in self hash A, so it gets translated into C is in hash of A. So hash of A has only B. It doesn't have C. So we don't go there. Then we go here for all of the keys. And the keys are just B. Key is not seen. So yeah, B is not seen. We add it there. So seen becomes B. Yeah. Then res is self-rec key be seen. So this time we are calling rec with B and C. So we also pass the same C in there. And we end up on the second iteration where we check A is B. No, it's not. Then this gets translated into C is in hash of B. Is it? C is there, yes. And it's 3. So we just return 3. Now we go back here and res is not none, it's 3. So we return self hash A and key in this case is B. So we return a hash of A and B multiplied by 3. And hash of A and B is 2. 2 multiplied by 3. So it's 6. We return that. That's exactly what I wanted, as I remember, right? Yes, it's there. Okay, let's look at this guy. A over E. And I think we have another case, which we forgot. It's this guy, X over X. But yeah, otherwise, if we don't have an extra check for that case, then we would end up having an exception here when we access a missing element in the hash. So we have to put the check here. If A is in self hash, is not in self hash, then return none. Yeah, so that's what we need for this guy, for X over X. So now we know that hash A is present, then we check if B is there, then we return AB, so those are valid guys. Then hash A again, we know it's there, and we know that key should be there. Yeah, so no out of boundaries anymore, or key missings. Then I wanted to check for a missing E, because we don't have E here. Let's try A over E. So we have same self hash. We just need to remove those guys, or let's say rewrite them a little bit. Okay, so let's see. We go here. No, it doesn't. It also doesn't pass. Then we go here. There is no direct connection between A and E. So we end up exploring all the directs of A, which we know is just, it's only B. So here B is not seen. We add it there, B. Then we calculate rec for B and E. So it would be B and E. So now we are here. A is not B. No, they are different. Then A is not in self-hash. And let's see. Actually, we could have just returned that immediately. Um, but yeah, what I'm thinking right now is that if we checked for E being present in self-hash, that would save us a lot of hassle, so we wouldn't have to go through all of those edges and stuff. But what I'm thinking is that if we had like a forest with two unconnected graphs, both of the nodes would be present there. For example, if we had that stuff and also E over E equals 1. So yeah, someone just passes E over E equals 1. Then this those three literals, A, B, and C, they would be in one graph of the forest, and then E would be in a separate, a single noded graph. They will not be connected, but E would be present in the hash. So let's not add extra checks here for that case specifically. Uh, we will end up solving that anyway. Okay, so we've been here, B and E. We checked B is present in self-hash, yes. So now we go here. B is in self-hash A. It means are they directly connected? No, they are not. And then we go here. So who is directly connected to B? Let's see. It's A and C. And C has weight 3. So it's A and C. But yeah, let's have them like that. Key first takes A as a value, and then A is in scene, so we don't go here. Then C is not there, so we add C in scene, and then we go in rec again. So we end up calling rec with C and E. So this E never changes. We only change A, which takes values A, B, and C. Okay, so now let's go again. Um, this guy fails, this guy fails. E and C are not directly connected. Then we have some direct connections of C. It's only B. So let's put here. K is in scene, so we don't go there because B is already there. And we end up doing nothing here, and we just go to the last statement, which is return none, and then we unwind the recursion back. So we go back here, blah 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 blah, we remove that stuff. So this result is none. Um, so we ended up going to return none again. So we unwind again. Uh, this guy returns none. So we don't do that. We go straight here to none. And that's it. That's our first call. And we end up here. Res is none. Return -1. Okay, so that should work. Now let's run code. Runtime error. Invalid syntax. Line 95. Wow. Why is that? What's wrong here? If A is not in, because I have is. Yeah. Okay, let's run it again. Yay, it's finished. And what's the result? 6, 3, minus 1, 1, minus 1. Okay, let's submit that stuff. Yay, accepted. And let's look at details. Yeah, we are somewhere here. Okay, let's see. What if we just modify our in case the one which I told you about, the E and forests and graphs and stuff. If we just add the check for that here, if um, let's actually do it here, or B not in self hash, then return none. First, let's try it here. It's finished, and then let's submit it. Yay! Accepted. More details. Yeah, we're a bit closer, I guess. I don't remember what was the last one, but we are not at the top. We are somewhere in the middle. So solution is not super optimal, but at least we are below 100 milliseconds. It's for 42. Oh, actually, that's the best answer ever. So I am really satisfied with that. Okay, guys, thank you for watching. Please subscribe and follow new videos. Good luck at your interviews. Feel free to leave comments. Bye bye.